All right, so we're going to finish up looking at sine and cosine, and we're going to be looking at graphing multiple transformations. Okay, what's very important, something that comes up when you do multiple transformations that doesn't come up when you just do a single transformation? Yeah, okay, you have to do things in a certain order. Okay, it's just like PEMDAS. If you switch the order you do it, it can come out different. Does anybody remember, based on like the kind of functions we've done all year, what's the first thing we always do? Yeah?
Isn't it the shift left and right?
Yeah, we always do the shift left and right, which in this case, we call it a phase shift. Trig functions is the only place I've seen it called a phase shift. When we use other functions like square roots and stuff, they just call it horizontal shift. All right, so we get our shift left and right. What's the second thing we always do? Yep?
Vertical stretch.
No, not the vertical stretch yet. That's going to come a little bit later.
Horizontal.
The horizontal stretch, okay? Which in a trig function, we call that a period change. Okay, so I can put those in. This is the horizontal shift. This is the horizontal stretch. And what's special about these two things? All the horizontal stuff. Yep?
Aren't they only affect x?
Yep, they both only affect the x values, but there's something you want to be very careful of when you have these two. Yep?
Do the opposite of what you expect.
Yeah, they do the opposite of what you would expect. All right, so when you see a plus with a phase shift, it actually shifts left. When you see a minus, it shifts right. Bigger numbers do not make it bigger. Bigger numbers actually compress it. Small numbers make it bigger. All right, and if we were going to study reflections, okay, over the y-axis, they would also be done right at this step. Okay, but we're not doing reflections over the y. All right, so that's all our horizontal. What's the first thing we do for vertical? Yep.
Stretch.
Yep. Do the vertical stretch, which, just like all the other functions, we call it a vertical stretch. It's a change in the amplitude. Okay. At this point, you can also do your reflection. Okay. So do reflection if necessary. It doesn't really matter if you stretch and then reflect or reflect and then stretch. They're both step 3, and as long as you do them together, the order you do these two in doesn't really matter. Okay, and then after we do our vertical stretch, what's the last thing? Vertical shift. Okay, so if we had a problem completely written out, let's just kind of label it and match it up with these numbers. Let's do bx plus a, c, and d. All right, so your phase, this is your phase shift. Okay, your period change is b. Your vertical stretch is c. How would you know if it's a reflection? Yep. If you had a negative with the c, that's your reflection. And the fourth thing is your vertical shift. Okay, so we just do each transformation one step at a time. Did I mess something up? A, B, C, D? No? Yeah, what's up?
So say, don't you need to make it so there's a plus or minus before the D because you're adding it?
Oh, yeah, thanks. Yep. So it's plus or minus D. All right, so we just, again, one step at a time. So you go through each one, and you use the same rules that I gave you. Okay, whether it's for the shifting or stretching, just follow all the same rules. Okay, any questions before we try an example? All right, so let's look at this one. 2 sine x plus pi over 2. Now, here you technically don't have to be as careful with the order. I would always recommend doing it in the order I just gave you. So when you do have to be careful, it'll take care of that. Does anybody know why in this problem the order really doesn't matter. Yeah?
Because the pi over 2 affects the x,
Mhm.
but the 2 affects the y.
Yeah, you're doing one transformation to x and one transformation to y, so they are separate. Okay, two separate things. It's not like you're doing two things to x and you've got to be careful which one you do first. So this order really comes into play when you have both 1 and 2 in the same problem or 3 and 4 in the same problem. All right, in this case, we'll follow the order, okay, just to get used to it though. All right, so which one do I do first? My plus pi over 2 or the times 2 in the front?
Plus pi over 2.
Yep. And what is that transformation?
That's it.
A phase shift. All right, so for now, we're going to start with all our y values the same. Okay, what are my y values for sine?
0, 1, 0, negative 1, 0.
Yep. 0, 1, 0, negative 1, 0. And now we're going to take all of our original x's, 0, pi over 2, pi, 3 pi over 2, 2 pi. And what are we going to do to each one of them?
Pi over 2.
Yep, we're going to subtract pi over 2. Right, so what's my first one?
Negative pi over 2.
Negative pi over 2. Second one?
0.
0.
Pi over 2.
Pi over 2.
Pi.
Pi. And
3 pi over 2.
3 pi over 2. Okay. Any questions on how we got that? All right, so now this table is going to be our starting point for the next transformation. Right? That's how we do it. So unfortunately, if we make a mistake at this step, it's going to mess us up for each table we make. All right, so this is sine x plus pi over 2. And now our final one is going to be 2 sine x plus pi over 2. Okay, what kind of transformation is the 2?
Vertical stretch.
Yep, that's a vertical stretch. So what's going to stay the same here when we stretch vertically? Fine?
The axis.
The x's. So I'm going to copy the x's from my previous table. Okay? So we've got negative pi over 2, 0, pi over 2, pi, and 3 pi over 2. And now what are we going to do to all of our y values? Yeah, we're going to double them. Okay, we're going to multiply all the y values by 2. So we get 0, 2, 0, negative 2, 0. And on the test, that's what I'm going to be grading, the final table. Okay? If in your head you can go to the final table right away, that's fine. Okay? If not, do one transformation, then do the next. Okay. Questions on that table? All right, so now let's just make our graph. All right, so we're going to be at negative pi over 2. Okay, 0. We're going to use that point, so I'm not skipping. Pi over 2. Pi. 3 pi over 2. Okay, highest value and lowest value I need are what?
2 and negative 2.
All right, so we can go 2, and you know what? Actually, I'll label it like this. 2, 0, negative 2. Okay, now just make your graph. We're at 0, and then we're up at 2, back to 0, negative 2, back to 0. Okay, just connect your points. Okay, so that graph has been shifted to the left by pi over 2 radians, and it's been stretched by a factor of 2. Okay, questions on that one? All right. So let's try this one. 3 cosine 2x plus 1. All right, so first of all, how many transformations?
3.
Yeah, we've got 3. What's first transformation I got to look at, Brian?
2x.
Yeah, I got to focus on this 2x, and what is that?
That is a horizontal stretch.
That's my horizontal stretch, or in this case, it'll actually compress. Yep. All right. All right, so Jacob, since we're going to focus on doing horizontal stretching and compressing first, what values stay the same?
The y.
Yep, I'm going to keep the y's the same. And Leon, what are my y's for cosine?
1, 0, -1, and 0.
1, 0, -1, 0, and 1. Is that what you said?
Yeah.
Okay. All right. And now x values. Okay. Matt, how do we use that 2 to figure out my x values? Yeah, we're going to divide all the original x values by 2. All right? So my first original x is 0. Divide by 2, and it becomes, yeah, so that stays 0. Okay, what's my next x value? Yep, it would have been pi over 2, but if you take half of it, it's pi over 4. And now, if you look at the pattern, what's the gap between 0 and pi over 4? It's pi over 4. So then we've got to keep adding pi over 4 each time. Okay? If you can, if you get like 2 pi over 4, just reduce it. So what's the next one? Pi over 2. Okay, next one? 3 pi over 4. And then the last one would be 4 pi over 4, or just pi. Right, so that one is cosine, I'll just label it. Cosine 2x. Okay, what's my next step? Yep, deal with the vertical stretch. And in this case, which number is that? That's the 3. All right, so for the vertical stretch, Cameron, what stays the same for vertical stretch?
The x's.
Yeah, anytime we can keep the x's the same, that's great, because then we don't have to deal with all the pi's. So copy those down from your previous table. Okay, don't go back to the original. You're going back to the table you just made. 0, pi over 4, pi over 2, 3 pi over 4, and pi. Okay, and John, what am I going to do to all my y values?
You can add 1. Or no, you. I'm going to go with 3.
We're going to do what?
Times by 3.
Times by 3, yeah. And what do you get if you times them all by 3?
3, 0, -3, 0,
3. Good. All right, so now we've dealt with the period change. We've done the vertical stretch. Last thing I got to do is deal with this +1. All right, Jean-Paul, do you think you know what the +1 does? I know you weren't here yesterday. We've already done horizontal stretching. We've already done vertical stretching. So it's not a stretch. It's a
Shift up or down.
It's a shift up or down. In this case, which way do you think plus is?
Oh.
Yep, plus is up. So we're going to now shift all our y values up 1. So we have 3 cosine 2x plus 1. All right, so we got x, y. Okay, I just said we're going to shift all the y's up. So keep the x's the same. 0, pi over 4, pi over 2, 3 pi over 4, and pi. And Brian, my new y values, what will those be?
It would be 4, 1, -2. I believe it's 1 and then 4.
Okay, and that is our final table. All right, so was the order important in this one? Yes. Okay, the reason order matters here is because we have two transformations affecting the y's. We're tripling them, and then we're adding 1. What would happen if you added 1 first and then tripled it? Just look at like this first row. Tell me what the final y value would have been if you added 1 and then tripled it. Would it come out to, yeah, it would come out to 6. Okay, what would end up happening is you would increase all these by 1 and then triple that, not only the original number, but you're tripling the increase by 1 with it. Okay, we don't want to do that. We want to just triple first and then add the 1 after. Okay, so there's an example where it makes a difference. Hey, any questions on that? All right, so let's make our graph. All right, so this time my highest value is 4, and my lowest value is -2. All right, so I think what I'm going to do is just add in one more line. Okay, and if you want, you can, I think going by 2's would probably work out pretty nice here. Okay, graph paper on the tests, you won't have to draw it yourself. It'll already be drawn for you. All right, so let's make this 0, -2, 2, 4. That should work fine. And my x values, I'm just going to label them pi using the ones I got right there. All right, so that's pi over 4, pi over 2, 3 pi over 4, and pi. Hey, now just graph your points. So we're at 0, 4. Pi over 4, we're at 1. Okay, so we put that right about there. Pi over 2, we're at -2. Back to 1. Back to 4. Okay, any questions on that one? Now we'll just make our sketch. And that's it. Okay, so on a test, I probably won't give you a transformation with all 4, but you might have one like this. Okay, up to 3 transformations in the same problem. Okay, questions on that one? All right, so why don't you try this one on your own? Okay, take a second. Figure out which transformation you should do first, which one you should do second. Okay, and then when you're done, look at it and see if the order really even matters at all. Okay, but just take a few minutes and give that one a try. All right, so this one we got 2 transformations, and what are the 2 we have to do?
Phase shift.
Yep, you got a phase shift and
Vertical shift.
vertical shift. So a phase shift is a left and right. A vertical shift is an up and down. So those don't affect each other. One's x, one's y. All right. So technically here the order doesn't matter, but it's always a good idea to follow that order just in case it does matter in some problems. All right, so Derek, what transformation do we do first?
You can do the minus pi over 2.
All right, we're going to deal with that phase shift. So y's stay the same. And what do I do to all my original y values?
You would subtract pi over.
Careful. So it's a phase shift. If we subtract pi over 2, it's going to go the wrong way.
Yeah, you would add.
Right, we got to add pi over 2. Right, so we're going to have pi over 2. Okay, what's my next one?
Pi. Subtract pi over 2.
Pi.
3 pi over 2.
2. 5 pi over 2. Okay, if you put a denominator of 2 here, you'd see a nice pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If you see that pattern, then that means you did something right because the spacing is consistent. All right, so that's just the phase shift. And now let's do the plus 5. Right, so when I do the plus 5, how do I handle that? How about Aiden? Yeah, just add 5 to all the y values. And what about the x's?
They just stay the same as 0.
Yep, just keep them the same. So 3 pi over 2, 2 pi, and 5 pi over 2. All right, so how about Kanan, what are my new y's going to be?
5, 6, 5, 4, 5.
5, 4, 5. Yep, looks good. 5, 6, 5, 4, 5. Okay, questions on that table? All right. Okay, so make our sketch. Let's see, we got to go up to 6. Okay, so that'll work. And we're going to start at pi over 2. All right, now I got to just check to make sure my spacing is consistent. If I put pi right after it, does that keep the spacing consistent?
Yes.
Yeah, that's fine. Okay, because you got a gap of pi over 2 and then another gap of pi over 2. So that's good. All right, and then 3 pi over 2, 2 pi, 5 pi over 2. All right, so pi over 2, we're up at 5. Pi, we're at 6, 5, 4, back to 5. All right, what's the amplitude of that function? 1. Good. Some people say 6, but it's not 6. Okay. Amplitude is if you imagine that center line, how high it goes off of it. Okay, so 1. What's the period of that function? Yep, 2 pi. We didn't change the period this time. Okay. So we didn't change the period. We didn't change the amplitude from the original. Okay. All we did was translate it up and to the right. Okay. Hey, questions on that? All right. So this one is not a graphing by hand. It says find a complete graph, so I'm going to look for a window. And then find the domain, range, amplitude, and period. All right, let's restrict that a little bit. Let's find a complete graph that shows 1 period on the screen, and then let's find a complete graph that shows 2 periods. Okay, and I'd like to try to find a window that doesn't chop a period in half. All right, so if I'm looking for 2 periods, of sine, I'd like to see something that looks just like that, not half and half on each side of the window. All right, so to do some of that, we might want to figure out some of these other things first, because our period is what's really going to dictate how big of a window do we need if I want to see 1 period, 2 periods, and so on. All right, so let's start with that. Okay, what's my period for this one? 2 pi over 3. Right, so we know that if we want to see 1 period on the screen, the difference between your x min and x max has to be this much. Right? If you want to see 2 periods on the screen, the difference between x min and x max would be 4 pi over 3. Right? So we'll come back to that in a second. What else they want? Right? Domain, range, amplitude. What's the domain here? All reals. Okay, for sine and cosine, the domain is always all reals. There are no vertical asymptotes. Okay, as I mentioned earlier, when we start to study tangent and the other trig functions, we're going to have to be careful with the domain. But here, it's all reals. How about the range?
Including them.
Yeah, what I usually do is think, okay, what would the range be normally? Okay, -1 to 1. Now you've quadrupled it, so it's -4 to 4. And then ask yourself, all right, did I shift it up and down at all? In this case, no. Right? If I shifted it up or down, I'd have to take that into account too. So our range is -4 to 4. Let's say you had a +1 on the end. Okay? All you'd have to do is +1 to each of these numbers. -3 to 5. Shift it up. Okay, and amplitude. Okay, What's the amplitude here?
4.
4. Okay, what if I put a negative in front?
Still
Still
4.
be
4.
It'd still be 4. If I kept the negative in front, would it affect the period?
No.
No.
Nope. Would it affect the domain?
No.
Nope. Would it affect the range? No. It wouldn't affect anything, okay, in terms of these values. It would affect the graph because it would flip, but it would still be between -4 and 4. It'd still have a height of 4, same period, same domain. Okay. All right, so now let's try to find a complete graph. All right, so what do we have? 4 sine 3x. Okay, and we're going to do it in radians. Right, so 4 sine 3x. All right, let's make sure we're in radians. Yep. All right, so think about sine. And where should I start it for my x min? Yeah? Yeah, I think 0 would be good because we haven't shifted left or right. If we had, maybe we'd want to take that into account, but in this case, we haven't. And if I wanted 1 period on the screen, what would I set my x max to? Yep.
2 pi divided by 3.
Yep. Just type 2 pi divided by 3. It'll change it to a decimal. Let's check the range. Okay, actually, I think my range here is fine. Okay, -4 to 4. Okay, so let's hit graph, and we should see exactly 1 period on the screen. No, it's perfect. Just barely fits, but that's fine. All right, so let's take our window. Okay, and that's our window for 1 period. Okay, this was 0. Okay, and now what if I wanted 2 periods?
You would just double the x max.
Yeah, just double the x max. Actually, no, I wonder if you can just go like this. Just take that and do times 2. Yes, you can. All right, so there's 1 period, and there's our 2nd period. All right, so that's the window. That would be a complete window for 2 periods. Okay, on a test, I generally wouldn't ask you for delta x, x scale, y scale. Okay, you don't need that. I would ask for the mins and maxes to fit it on the window.
And how would you have us rounded?
For your window, I would probably say just keep it exact.
Okay.
You know, I would keep it as 2 pi over 3, 4 pi over 3, things like that. Yep. Okay, any questions on that one? All right. Okay, so let's try this one. Find a complete graph of 3 sine x minus 1, then find domain, range, period, and amplitude. Okay, I like to find these things first and then go back and do the complete graph, because knowing the period is going to help me to do the complete graph. All right, so let's start with our domain. Okay, what's the domain here? Yeah, for sine and for cosine. Domain is always all reals. Okay, what about my range? Think of what it would be before we do this transformation, and then do that to it. Brian?
Bracket -3, 3.
Yep.
Bracket.
Good. So there's my domain. Yeah. Domain, range, period. Okay. What's my period? 2 pi. We haven't changed anything there. And what else? Amplitude. What's my amplitude? 3. All right. Now, if I set my window from 0 to 2 pi, will that show me 1 period?
No,
No, because
this is the shift.
Well, what's the period here?
2 pi.
The period is 2 pi.
Period, but it could be like,
Yeah, 2 pi is the distance between the two. It's just that that's not where it's set to. It's between 0 and pi
Well,
because you got shifted off.
they'll give you like, actually no, because it's half. Wait.
So if I'll fix my y equals in a second, but if I just do that, will I get 1 period on the screen?
No, you will be. Well, it might be a full period, but it might be split up.
Yes.
Yeah, it will be a full period. It's just, it's going to have a little section of like the previous period and a little section of the next one. Okay, if you want to think of it that way. So it's going to look a little bit off.
It's just that it's not all solid.
So 3 sine. So in a second, I want to think about a window that would give me a really nice looking picture. All right, so again, technically that is 1 period of sine, but it's not the best way to look at it. I'd kind of like to look at it starting right there. Right? Or we could shift it enough so we're somehow starting at 0. Right, so I'm going to have to adjust my x's. Okay? How would I adjust them to get a nice look on the screen? Yeah?
I would trace so you can find where that first point is.
All right, so we could go on the graph and we could trace. Yep. It might take a little while to
Or like you
trace over and
oh no, I was saying that first point right there on the 0.
But- oh, after 0. I'm sorry. You want to go this way.
Yeah.
Okay.
And then you find that point.
So it looks like it's about 0.999. But how could we have gotten that just by looking at the graph itself? The tracing is fine.
Well, you know, when this is x minus 1, you're shifting to the right 1. So you would just make your first x 1.
Yeah, it's basically, if this is your original period, okay, 0 to 2 pi, you've taken that window and you've shifted it to the right 1. So make this 1 and make this 2 pi plus 1. If you make that your x min and max, you're going to get a nice window. All right, so the first one, we can just type in 1. For the second one, I'm just going to type 2 pi plus 1. So yeah, you can do arithmetic right in your window, and it'll change it to a decimal. Now we get a nice graph. Okay, there's nothing wrong with doing 0 to 2 pi if the directions just say graph a complete period. It's just, I think, and probably most people would agree, that this is a nicer look because you're not chopping anything off. Okay. Questions on that? It does take a little bit of practice to get used to how you need to set it to do that. Again, if on a test I asked you where to round, I would leave this at 1, and I would just, I would just say this is 2 pi plus 1. There's not really much you can do to neaten that up. Okay, y min and y max, they're a little bigger than they need to be, but I wouldn't mark that wrong. That's fine. What I would mark wrong is if you had like -2 to 2, because then you'd be cutting off part of the graph. Okay. Any questions on how you would extend this to see 2 periods? Right? If you get stuck, I'd say, well, I want to, instead of go 0 to 2 pi, I want to go 0 to 4 pi, but then shift that whole thing 1 unit to the right. So it would be 1 to 4 pi plus 1. And that would give you 2 periods. All right, so I might have mentioned these two identities, and we've seen them when you draw sine and cosine, that if you take sine and shift it pi over 2 radians to the left, it becomes cosine. Or you can look at it the other way. take cosine and shift it pi over 2 radians to the right, and it becomes sine. Okay, so these are called horizontal shift identities. So what this would allow us to do is we could take a problem that has sines or cosines in it and change it to something else. Right, so let's say I had a problem like sine of, you know what we could do? We'll do it in degrees. Let's say sine of, I don't know, 50 degrees. Okay, if we wanted, we could rewrite that as a cosine. Okay, what would that be the same as? As a cosine.
50 degrees minus pi over 2.
Yeah. Just pretend like you're plugging 50 in right there. So we could write cosine, if you're doing it in degrees, negative 40. And even better, does anybody remember what happens when you have a cosine with a negative? It's the same as a positive. Okay, we looked at the symmetry when we first started graphing. So the sine of 50 and the cosine of 40 should come out to exactly the same thing. Okay, let's just check it. Right, so sine of 50 and cosine of 40. Yep, same thing. Okay, why would we want to change sine to cosine? We might be doing a problem that had other cosines in it, and maybe that would help us to do some combining of like terms or something like that. All right, so you don't just have to use these for graphing reasons. You can use like basic trig arithmetic stuff too. All right, so for now we're going to practice solving these on a calculator. Eventually we're going to solve these by hand. But what do you think is going to happen when you solve a trig equation in terms of the number of solutions you get? Any thoughts? Yeah? Yeah, you really, if you have one solution, you have infinitely many, all right? Unless they give you a restriction on the interval they want you to look for solutions in. But you really have infinitely many. Okay, how could I solve this problem? How would I type that in?
Would you do the sine and negative first power thing?
Okay, if we were going to solve by hand, we would be using inverse sine. Yes, but for this, all I'm going to do is show you guys how to solve it on the. Oops, I don't really want that. On the calculator. Okay, so how would I type this in so I can solve it on here? Fine.
Would you actually have to, like, in a way, set up as two separate y values? Or, yeah, no.
You mean y equations?
Like y equations,
Yeah. How would you do that?
Like I was just say, it would be y equals sine of x, and the other one would be y equals 0.4.
Yeah. And what are you going to be looking for? Yeah, we're going to look where they intersect. Okay. Since they gave me a specific window in a second, I'm going to set my x values to what they told me to. But if I do zoom 7, okay, and you know what? Let me change to radians because this problem is in radians. I can tell because of the 2 pi. All right, so let's just go mode, radians, and then do zoom 7 again. And if we were to look at this wave forever, how many times would that red line intersect it? Infinitely many. Right? So the idea is we'd only have to find maybe 1 or 2 solutions, and then we could just say that those solutions are going to keep reoccurring every period. Okay? So every period you get another solution. Okay? In this case, they only want us to list all the solutions between 0 and 2 pi. Right, so that's what I'll do. Okay, so it looks like we're only going to get 2 solutions. And someone remind me, how do we find intersects? You haven't done that in a little while. Second Calc 5. Yep. All right. Do this one since I'm right next to it. So we get about 2.73. And does anybody have the other intersect? All right, so it's fine. Find that one. Okay, that should be close enough. Okay, 0.41. Right, now, Autumn, what did you mention earlier about? You were mentioning like a different way to solve that.
It would have been like that. If you would have calculated. Oh, a different.
Yeah, you mentioned something different.
You would have put inverse sine of 0.4,
Yeah.
and then it should come out with one of those.
Yeah, it'll come out with one of those. Okay, it gives me the 0.41. We're going to talk about if you use the calculator and you have the 0.41, how do you get the 2.73? Well, really it all depends on the quadrant that your answers are in. Okay, so we'll talk more about that when we get closer. Yeah.
Oh yeah, for the x scale where it's like 1.57, how do you like get so it's that calculation?
I just did zoom 7 and it filled that in. Does anybody know what is 1.57 really in terms of pi? That's pi over 2. So what the calculator is really doing is putting a tick mark every 90 degrees, or pi over 2 radians. Yep. All right, and these answers usually come out messy. I wouldn't try to write 2.73 or 0.41 in terms of pi. Okay, unless the line happens to cross it like right at the highest or the lowest value, or sometimes we can, but usually we can't. Okay, so any questions on that? All right. This is really giving you the same window. They decided to write it. Well, you can write it that way, but you have to flip these signs. Okay, so they want answers between 0 and 2 pi. Okay, bigger than 0, but smaller than 2 pi. All right, so Leon, what would I type in y1?
Cosine half x for the first one.
Close. Not missing one thing though.
All right.
What else is in front of cosine?
Oh,
2.
2. I thought that was the example.
Right. So 2 cosine, just to keep it easy, type 0.5x. And then in y2, what would I type in? 1.5. If I forgot this 2, okay, what would happen? How high and low, what would be the range on cosine if you forgot the 2? 1 to -1. Well, if you try to find where the graph hits 1.5 and it's always between 1 and -1, we would have no solution. Okay, so I had to put the 2 in order to make this problem work.
Now, what if you divided the 2 out from 1.5?
You could say cosine of half x equals 0.75.
That would still work.
It'd be the same problem.
Okay.
And if we were going to do it by hand, that would be our first step. We could put the 2 on the other side. Yeah, but since we're just graphing it, that's fine. Okay, keep your window from 0 to 2 pi. Let's check our range. Yeah, we're going to be fine on the range. And graph it. All right, so this time we only got one answer in the interval they're looking for. Okay, that's fine. Second calc intersect. And we get about 1.46. Now, did we graph a full period?
No.
No, they didn't ask us to. Okay, what would be a full period here? 4 pi. Okay, it would be this 1/2 causes it to stretch. So normally, if you wanted to see a full period, we'd have to go to 4 pi, and I think you would get another answer. Okay, so how often is this answer going to reoccur?
Infinitely.
Well, what would you add to it to get the next time you'd see this answer?
Pi.
No, this answer is not going to reoccur every 2 pi. It's going to reoccur every 4 pi. All right, so if you add 4 pi to this number, you would get the next time this occurs down the graph. Okay? If you subtract 4 pi, you could get the time before it. Okay. Right. So any question on that one? You don't have to worry now about how often it reoccurs, but eventually you'll have to worry about that, but not today. Okay, this one is basically finding where two trig functions cross again. Let's just graph it, see what happens. Okay, when we start trying to set trig functions equal to each other, that can be tough to solve by hand. Okay, if you just got a single trig function, that's not bad. Okay, but multiple trig functions we'll do some, but they have to work out nice. Okay, if you didn't want to do y1 and y2, what could I do to this first and put it all in y1?
You turn sine of x into cosine of x plus pi over 2.
All right. If we were going to solve by hand, we might want to try to look at changing sine to cosine somehow. But if we're going to graph it on the calculator, it's okay to keep sine and cosine. But I would have to do something with one of the sides if I wanted to put it all in y1. What would I have to do? Yeah? You would what? Careful, not divide, but subtract. Okay, if you wanted to put this on the other side, you could minus it. Okay, and what that would do is it would actually show us what this graph looks like. Okay, right now, we're not going to see what this would look like. We're going to graph two separate things and see where they cross. All right, so let's do that. Okay, they wanted 0 to 2 pi, so we're good. And how many times does it look like they cross?
3, 4.
Yeah, I think it's 3 times. 1, 2, 3. So you'd find all 3 x values. Okay, find all 3 x values. Okay. Any question on how to do that? Okay, I want to show you what this graph looks like if you move everything to one side. Okay, so I would subtract 2 sine x. So it would become what's in y1 minus what's in y2. I could type that all in by hand, but that's just quicker. Okay, I'm going to turn off y2 and y1. So it's going to graph 3 cosine 1/2 x minus 2 sine x. And now you'll actually see what that looks like. Right, so it kind of looks a little different than what we've seen before. Okay, it kind of has this. It dips down, then it goes back up, then it dips back down. And this pattern would keep repeating. So if I went out to, let's say, 6 pi, you'd see it repeat a few times. Actually, I think you're seeing it repeat almost.
1.5.
Actually, I don't even know if we're seeing it repeat yet. Okay, I'm not sure. What did I go to? 6 pi? go to 12 pi. Yeah. Right, so we got that section that dips down, and then now I think we're seeing it repeat.
Yeah.
Now we are.
There's
Yeah.
3 of them.
There's like.
All right. So there's
3.1.
yeah, there's a bunch. So there's a definite pattern, but when you start combining trig functions, it starts to look really, really different. Okay, and that's how some of the frequencies we talked about on the phone yesterday, they would look if you drew them. Okay, that's what I was playing with earlier. Okay, because you're combining multiple trig functions at the same time. We won't be sketching these by hand. Okay. But either way, do your intersects or get it equal to 0 and then find the roots. Okay, either way will work. All right, and last one, pretty much the same idea except it's an inequality. So this time my answers isn't going to just be a number. What will my answer be?
X is greater than,
Yeah, it's going to be an interval. Okay.
or
Yep, some kind of interval. All right, so I'm going to graph 2 cosine x, negative 1.3. Notice just by me retyping something in, it turned them back on. Okay, I had shut them off, but if you type something new in, it'll turn your graph back on. And 0 to 2 pi, so I need to set my window. 0 to 2 pi. All right, so we're looking where the cosine function is above negative 1.3. All right. So how would we do that? Yep, we'd find the intersects.
from 0 to the first intersect value.
Let's just call this one A, comma, negative 1.3. We'll call this one B. I know the y value is negative 1.3, but you'd have to find the x's.
Would you put like the U in between?
Yep, there's going to be a union here. And what's going to be my two intervals?
It'll be 0, A, and then B, 2 pi.
Yep, from 0 to A, including A or not?
No.
No. We can't include A because it said strictly greater than. And what about my interval for the second part?
Not
B,
included.
2 pi.
Not including B. Including 2 pi or not?
Not.
Not including 2 pi because it doesn't.
Right.
Oh, okay.
Not including 2 pi because of the restriction they gave me. Right, so you just have to find what the two intersects are, and that would be your answer. Any question on how you find those? All right, so that pretty much finishes up everything that we're going to do with sine and cosine. Next time we'll look at the graphs of the other 4 trig functions, but we're not going to go into as much depth as we did with sine and cosine, because we're going to do all 4 in the same day. All right, so this time homework is in the book, so if you want some graph paper, you can grab it. Okay, this is page 346, 2 through 4, 7 through 10, 15, 17, 21 to 23, 29 to 32, 36, 39, and 43. They're not all graphing. Okay, some of them are just calculating intersects. Some other ones are just finding domain, range, that kind of stuff. Okay, but I think that the early ones are graphing.